The next portion of 6.2 will cover how to find the mean, the standard deviation, and the variance along with the shape of the binomial distribution. Just like in section 6.1, when we're looking for the mean of a probability distribution, we are trying to find what is called the expected value. So here we are going to practice finding the mean of a binomial distribution. So if we have an example of a 10 multiple choice question quiz, and if you have 5 choices on the quiz, that means the probability of guessing a correct answer would be 20% for each correct guess. And so therefore, if we were to calculate using the formula seen here, the mean is equal to n times p. And so if we have 10 questions, the probability of guessing correct would be 0.2, and if we did that multiplication, we'd end up with 2, which means that the expected value or average that a person would receive by guessing on all 10 questions would be a 2 out of 10. This slide shows the formulas for calculating the standard deviation. Sigma x would be the square root of n times p times 1 minus p, and then the formula for variance, sigma x squared, would be n times p times 1 minus p without the square root. These formulas, just like the mean from the previous slide, are found on your formula card that you are permitted to use on tests and quizzes, so you do not need to memorize them. This slide shows an example of the quiz problem that we were discussing earlier. If we had a 10-question quiz, so n equals 10, probability of guessing correct would be 0.2, and let's say x is equal to 6. We want to see if we could guess or correctly 6 on 6 out of the 10 questions, which would mean we would pass the quiz because that would be a 60%. So if we did the mean formula like we did earlier, n times p is 10 times 0.2, we get 2. So this is the expected value, what we would get if we were guessing. Definitely not a 6. The variance, n times p times 1 minus p, 10 times 0.2 times 0.8 is 1.6. And then the standard deviation using the square root formula or the square root of the variance, you would get 1.26 for the calculation. So if we take into consideration, think way back into chapter 3 when we talked about the empirical rule, if we wanted to pass, which would be a 6 out of 10, and a standard deviation is 1.26, and so if we looked at the average is 2, we want a 6, we are 10 standard deviations away from the mean. That would make it merely impossible, but not exactly impossible, just merely impossible. The next topic is discussing the shape of the binomial probability distribution. And if we use the formula to look at 3 different situations, we're going to look at what happens if we have a probability below 0.5. We're going to see the histogram will be skewed right. If we have the probability equal to 0.5, the histogram will be relatively symmetric. And with a probability greater than 0.5, the histogram will be skewed left. This picture shows us a histogram for a probability distribution that's binomial with a probability of success equaling 0.2. Now, if we have an experiment that we're repeating with n equals 10 trials, and we do multiple experiments every time having 10 trials, based on our previous formula, we would expect to see 2 as the average. And if you look at the histogram, you can see that 2 is definitely the most common, and as you get higher and higher, you get less and less probabilities of successes. And if you look at the shape, you can see that this is skewed right. And if you think about it, this makes sense because if a success is only 0.2, you should see most often successes around 2, 3, or 4, and that's what we see in the histogram. In this example, we see a binomial experiment repeated with trials n equal 10. This time the probability of a success is equal to 0.8, and using our formula, the mean is 0.8, and if you look at the histogram, you can see that 8 is definitely the most common. And we can see the skewed left shape in this histogram, which makes sense again because if 8 is our expected number of successes, then we should see a lot close to 8, like 7, 8, and 9, and a lot fewer way down at the 0, 1, and 2 range. The final histogram shows us a symmetric view where probability of a success is 0.5, which would mean we have a 50-50 chance of being successful or not being successful. And with the probability of being 0.5, it makes the mean 5, meaning the expected number or the average would be right around 5, making the most common observations around 4, 5, and 6, and the least common way down in the 0, 10 range. And therefore we see the symmetrical shape of the histogram. Now in the previous examples, we were always using an n equals 10 sample size. And for this particular slide, we're going to compare what happens with the same probability of success if we increase the number for n, meaning the number of trials. Now the first slide here is, or diagram here, shows us n equals 10 with a probability equaling 0.2. And we saw this earlier, this was a skewed right distribution. And so if we go to the middle graph, we see a n increasing to 30, meaning we're repeating the trials 30 times versus only 10. And then the final picture, we increase it all the way up to n equals 70. And one thing that you should notice is that the more trials that we add, even though the probability of success is only 0.2, we start to increase this into a bell-shaped or symmetrical curve. And in summary, what this tells us is that if you have a high enough number of trials, your distribution will always become normal. And this becomes important when we get into chapter 7.